Hi everyone, in this video I'm going to show you the collab where we compare Jax versus PyTorch. In the first markdown you can see the summary table of all 7 operations that we have covered in the notebook plus next steps and a Jax versus PyTorch comparison. In the next cell you can see we have a full Jax cheat sheet, arrays transformation, trees, flags, optex and train state patterns. As you can see in the output, we have a Jax cheat sheet. In the next cell, you can see we have a comparison table of NumPy versus PyTorch versus Jax primitives versus flags plus 8 Jax best practices. We have the comparison table and Jax best practices here 1 to 8. Then you can see in the next cell, we have a markdown intro to part 7 comparing the 4 approaches. In the next cell, we have full flex demo, defines flexible MLP, trains it on a 2 moons dataset for 200 epochs, plot training or value loss and the data. In the next cell, you can see same flex pipeline applied to the ZOR problem, trains for 1000 epochs and prints predictions for all 4 ZOR inputs. In the next cell, we defines the complete flex training pipeline, flexible MLP, create train state and train step flex. This explains what train state holds. In next cell, we shows available optex optimizers and print the 5-step optex usage pattern that you can see. Next is a markdown intro to part 6. This introduces flex linen and compare it to the primitive approach. In the next cell, we import for part 5 plus define binary cross entropy and flexible MLP, train MLP. Then solve ZOR problem using raw JX primitives end to end. As you can see here, ZOR problem, primitive network. The graph comparing epoch versus loss. Then we have training loop. Here we have defined create train step. This is and train MLP. This is the full training loop that you can see here. Then we define init and MLP params. There we are initializing and MLP forward. This is forward pass through a list of layer dits. We test it on the layer sizes 2841 network and then we define three loss functions. As you can see here, MSE loss, binary cross entropy, categorical cross entropy. We test MSE and BSE on same values. Then we define common activation functions from scratch: sigmoid, tenet, ReLU, leaky ReLU, softmax. Then we have a markdown intro to part 5. This explains Jack's functional programming style. Params are passed explicitly, not stored inside a model object. Then we have gradient descent. minimizes fx is equals to x minus 3 whole square plus 1. We are using this equation and using gradient descent. Then in this, using this cell, we plot the graph of loss curve and the descent part on the function. In the next cell, we show that grad works on nested dicts. PyTrees defines a two-layer network as a param dict and compute gradients, and the output has the same structure as input. Then we demonstrate value and grad gets both the loss value and gradient in one call more efficiently than calling them separately. Then we show basic grad usage on function x square plus 3x plus 1. This also demonstrate higher order derivative by chaining grad of f, like you can see here. Then we have a markdown intro to part 4. Autodiff explains that grad returns a new function. It is composable and support forward and reverse modes. Then okay, then we have installs for setup and imports for jacks, flags, optex, import or libraries, configure plot style, print versions. As you can see in the output, we have version for jacks version, flags version, optex version, uh, and available devices, and create the initial PRNG key. Then we have a markdown to explain part 1, explains jacks.numpy as a near drop-in for numpy, with the key difference being immutability and .at syntax. Then we create jacks array 4 ways, from list, from numpy, and then using special arrays and using random keys. Here you can see in the output we are creating jacks array with 4 ways. Then we have a functional randomness where we explain Jack's explicit PRNG system shows that you must split a key before use, and that refusing a key gives identical results, and how to generate multiple key at once. This is the part that is covered in this cell. Then we list common Jack's D types and show how to convert those. As you can see here, convert between them with .as type, .node checks default to float 32, not 64. In the next cell, we show device management. This shows Jack's automatic device placement. In the next cell, we show array operations, element-wise operations, plus multiplication, sum, and all mirroring NumPy syntax. Then again in the next shell, we show the .at syntax for immutable array, update, set, add, multiply, and slice based updates. This demonstrates building a diagonal matrix functionality, as you can see in the output. Then we have a markdown intro to part 2. This introduces the 4 JAX transforms, JIT, grad, VMAP, PMAP, and emphasizes they can be composed. Then we have in the next cell just-in-time compilation. This benchmarks JIT versus no JIT on a heavy function. First call is to show slow compilation, subsequent calls are faster. In the next cell, we introduce a VMAP. A function written for one vector is automatically batched over a whole matrix, shows the result matches a manual loop exactly. Then we have advanced usage, advanced VMAP. This uses in access to mixed batches and non-batched arguments, and out access to control output shape, and double VMAP for batching both matrices and vectors. Then we have composing transformations where we compute, for example, gradient efficiently, showing a capability that is difficult to achieve in PyTorch without explicit loops. In the next markdown, we explain intro to part 3. This explains E in some notations. Letters represent dimensions. Repeated letters are summoned. Output shape is after arrow. E in some fundamentals. This cell demonstrate basic E in sum, transpose, total sum, column, row sums, diagonal extraction, and trace. Next cell shows product and multiplications. This cell shows E in sum for dot product, outer product, element-wise multiplication, matrix multiplication, matrix vector multiplication. And then in the next cell, we have batch operations, batch, matrix multiply, and transformer attention patterns. Then we have attention scores, and we have applied softmax and multiplied by 5. In the next cell, we have cheat sheet for ensum. This print a concise ensum cheat sheet mapping operation names to their ensum strings and numpy equivalent. So this was all about this notebook. Thank you for listening to this video.